In this last video here, we should be able to wrap up section 3.3, and we're going to end with synthetic division and a couple theorems. There's a nice shortcut for long division of polynomials by divisors in just this form: x minus some number k. This shortcut is called synthetic division. The pattern for synthetic division of a cubic polynomial is summarized as follows, and the higher degree polynomials will be similar. So first we figure out what it's. We have our cubic first as some number a x cubed plus some number b x squared plus some number c times x and plus d, and we're dividing it by x minus k. So we would rewrite it like this. Ignore all the variables in all the x squareds and x cubes and everything else. Just bring down the a, the b, the c, and the d, just the coefficients. This number here, remember this is always in the form x minus k. So if that is also or if this would happen to be a plus, that would be like x minus a negative k. I always thought about it like this. I'd concentrate on this sign, whatever's in front of that, and I would just switch it. Here we have a minus k because that's the format we're looking for. So I would change that minus here to a plus. And it would be vice versa. If that was a plus, I would make this a minus k, a negative k. So and here is the pattern that it follows. Whatever there follows, the first coefficient comes down. Then you multiply k times this is ka. And then you add. You add these two together and get this number. K times that number bounces up here. And whatever that number is, again, you add it to C. You get the result down here. K times that is equal to this. And again, you always add. That's the beauty about this. You know, you're multiplying and adding, the two easiest of the arithmetic operations. So you're always adding terms and multiplying by whatever k is. This algorithm for synthetic division works only for divisors in this form. Remember, x plus k, again, I already talked about that up here, is x minus a negative k. So, you know, if that's a little confusing, that's okay. Wait until you see it in action, and you'll see how easy this is. And you might be a little mad that I tortured you with the long division before I showed you this synthetic division shortcut. So let's see what we got here. In the first one, we're going to divide x to the fourth minus 10x squared minus 2x plus 4 by this, x plus 3. So the first thing I want to do is figure out, am I missing any terms, and write everything in descending order. Yeah, I'm missing x cubed. I got a squared, I got a first power, so yeah, I'm just missing an x cubed. So let's write the coefficients down. If you don't see a coefficient, there is an implied 1 there. So that would be 1 x to the fourth plus 0x cubed minus 10x squared minus 2x plus 4. And I'm going to divide that by this. When I look here, I concentrate on just this. I see a plus 3. I'm going to change the sign, so over here it is a minus 3. You know, if you want to think about it this way, x plus 3 is really could be rewritten as x minus a negative 3, and that negative 3 is what's going right here. So I draw a little line below. We just need one space here, and here's the pattern. Drop down your first number, 1. Negative 3 times 1 is negative 3, and you add, minus 3. Negative 3 times negative 3 is positive 9, and you add. Negative 10 and 9 is negative 1. Negative 3 times negative 1 is positive 3, and you add. Positive 1. Negative 3 times 1 is negative 3, and you add. So that turns out to be a positive 1. The last thing here, of course, will be our remainder. I'll just abbreviate that with an r. So let's put it back into polynomial form. We started with an x to the fourth, and we divided by an x. Well, x to the fourth divided by x is x cubed. That's where this will start. 1x cubed minus 3, we drop down to x squared, minus 1x, plus 1, with the remainder of 1, so we can write that remainder as 1 over x plus 3. And now it's back to polynomial form. Isn't that slick? So that is synthetic division. Again, strip away the variables, change that sign, multiply and add, and then put your x's back in there. Again, to find your leading term, take whatever that highest power was divided by this power. That will be where you begin, and then you just work your way down. All right, a couple theorems to talk about here real quick. The remainder and factor theorems. The remainder obtained in the synthetic division process has an important interpretation, as described in the remainder theorem. And this remainder theorem says if a polynomial f of x is divided by this x minus k, the remainder is f of k. For a proof of this, you can see proofs in math in page 327 in your book. The remainder theorem tells you that synthetic division can also be used to evaluate a polynomial function. That is, to evaluate a polynomial f of x at some value of k, divide by x minus k. The remainder will be f of k, as we're going to see here in this next example. So it says, use the remainder theorem to evaluate the function at x equals -2. So first, we're going to do the synthetic division part of it. Let's check that out first. So let's get our variables stripped away. We have a 3x cubed. We have an 8x squared. We have a 5x. And we have a -7. So all powers are accounted for. No placeholders required. And we are going to divide that by -2. Now here we're not switching the sign. If we had x equals -2, I could add 2 to both sides and we would get x plus 2. That's kind of what we're dividing into here. So that's where we'd switch the sign. Again, they just handed us x on a silver platter. So we're going to divide -2 into this with synthetic division. So follow the pattern. Bring down the 3. -2 times 3 is -6, and we add 2. -2 times that is -4, and we add 1. -2 times 1 is -2, and we add -9. That -9 is our remainder. So what is this telling us with the remainder theorem? If polynomial this is divided by this, then the remainder is r equals f of k. Or if we take this number, whatever it is, and we plug it into the function, the remainder pops out. Here it is in action. So if I take this -9 and I plug it in here, f of -9 is equal to, my bad, back up. We're not plugging the remainder in, we're plugging in this value. If I plug that -2 into the function, f of x, so that's my bad, I got a little ahead of myself, f of -2, I'm going to run that -2 through this part of the function. So we're going to have 3 times -2 cubed plus 8 times -2 squared plus 5 times -2 minus 7. And I guess I'll need a little bit more room. Let me just write up here. Our remainder was equal to 9. That's the important part. So let's figure out what all this is going to turn into. Again, we're evaluating f of -2. Well, let's see. -2 cubed is -8 times 3 is -24. Plus -2 squared is +4 times 8 is 32. And then we have 5 times -2, that'll be a -10. And then we have another -7 at the end. Well, -24 and 32, well, that adds up to 8. -10 and -17 is -10 and -7 is -17. 8 minus 17 is -9. And that's exactly what our remainder was. Or was our remainder +9? No, that was a -9, because at the end of our synthetic division, we had a -7 and a -2, and that added up to a -9. See, I just forgot the negative on there. So that remainder theorem says, we divided this into the polynomial, and our remainder was -9. Well, if we plug that -2 into the function and evaluate it, out pops the remainder, -9. And another point is, if f of -2 equals -9, what does that mean graphically? Well, graphically, we at least know the point on the graph is we do have a -2 comma -9 point. Why did my parentheses come out like that? If we were to graph this, we would see the point, or this graph go through the point -2 comma -9. That would be a little bit over here to the left and then down to -9. Somewhere down here is a point at -2, -9 that this graph will go through. So that's what that remainder theorem is saying here, with this sort of math jargon. If a polynomial f of x is divided by some factor x minus k, then the remainder r is f of k. So you took this number and you plugged it into the function f of k. And we also have another theorem, the factor theorem. Another important theorem is the factor theorem stated below. This theorem states that you can test to see if a polynomial has x minus k as a factor by evaluating the polynomial at different values of k. If the result is equal to 0, then x minus k is a factor. That just means there's no remainder, so it would divide in there evenly. And here it is stated officially, a polynomial f of x has the factor x minus k if and only if, the biconditional way back from geometry, if and only if f of k is equal to 0, which means, again, it divides evenly. There is no remainder. So we can use that to factor this. We got this huge polynomial, 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18. If it was a nice quadratic, we could just come up with a couple empty sets of parentheses and figure out, x times x is x squared, and then work on our middle term using the factors of our last number there. But this would be incredibly hard to try to factor, by trial and error. Luckily, they gave us some clues. Oops. X minus 2 and x plus 3 are factors of this. And if we take away this last term here, 18, how can you break down 18? Well, 18 is 9 times 2. 9 you can break further down into 3 times 3. So 3, 3, and 2 are factors of 18. It makes sense that, a couple of those might be, perfect factors that will have a 0 remainder. So it says show that these are factors of this big polynomial beast here, and then find the remaining factors. So we're going to take this big polynomial, 2x to the fourth. I'm going to write a little smaller here because I know I'm going to need the room, plus 7x cubed minus 4x squared. Ooh, and why am I doing it like this? Should we do synthetic division? Why not? Why was I even going to go the old way? Okay, so the coefficients. We have 2x to the fourth, 7x cubed, minus 4x squared, minus 27x, and a minus 18. We are going to divide. Well, which one of these should we do first? Does it matter? Not at all. Let's do this one here. X minus 2 is a factor, so let's change that sign to a plus 2. And we're going to divide that into this with synthetic division. So bring down the first term, 2. 2 times 2 is 4. And then we add 11. 2 times 11 is 22. 22 minus 4 is 18. 2 times 18 is 36. Negative 27 and 36 is 9. 2 times 9 is 18. And look at that. When we add there, we get 0. So 0 was the remainder, and we know that x minus 2 is a factor. So what we have here is, we know we got x minus 2 times, oops, that's not very good. We started with an x to the fourth. We divided by an x, so this would be starting with a cubed. 2x cubed plus 11x squared plus 18x plus 9, 0 remainder, so we broke that down. Okay, let's keep going. I guess I can get rid of a little bit of this and move this up. And now we're going to divide again. So let's bring our coefficients down. We got our 2, 11, 18, and 9. This time we're going to divide by, here's our factor x plus 3, so this will be, change the sign to a minus 3. And we bring down the 2. Negative 3 and 2 is negative 6. Add there, we get a 5. Negative 3 times 5 is negative 15. Add, and you get a 3. Negative 3 times that is negative 9. Again, 0 remainder. So we started out, originally, we had a factor of x plus 2. And now we have this factor of x plus, excuse me, that was x minus 2. Got it right up here. X minus 2 is a factor. And now we divide it again by x plus 3. Plus, and now we're left with this. We started out with a cube divided by an x, so this will start out with a squared, 2x squared, plus 5x, plus 3. 0 remainder. Okay, so we used the clues they gave us. X minus 2 and x plus 3 were factors. We divided them out. Again, it doesn't matter what order we did them in. We would still get to this same point. And now that we've gotten it this far, we can completely find the factorization by just concentrating on this and maybe using a little trial and error. So, don't forget these factors do come along for the ride, x minus 2 and x plus 3. But now we want to break down this remaining quadratic into 2 more factors. Well, the factors of 2x squared have to be 2x and x. The factors of 3 are 3 and 1. We just got to figure out where they go, so when we FOIL, we get the middle term of a plus 5x. And we've done that way back at the start of the year. It turns out here we want a plus 3 and a plus 1. So there is the factorization of this. Of course, we needed the clues to get us started. But if we were to FOIL all this out, so to speak, we would get right back to the original polynomial. Graphical solution on that one. Again, if we busted out the T99s, we can graph this up. From the graph of that polynomial, you can see that there are 4 x-intercepts. Again, it is a 4th power. It's even, so it will be going sort of like a parabola up to the left and up to the right. But all these other terms, the cube, squared, and x term, put some kinks and twists into the middle of that general shape. Again, if it's even, x squared is just a parabola up. X to the 4th will also be a parabola up. Again, but the later stuff did some twisting and turning in the middle. So if you did graph it on your TI-89, you would see that there are 4 x-intercepts. These might be easy to pick out. The 2, 0 and the negative 3, 0. Those are nice whole numbers. But these other ones in between there might be a little harder to find. The 4 x-intercepts are at negative 3, negative 3 halves, and negative 1. Again, if I went back to here, if I set this equal to 0, I would subtract 3 from each side and then divide by 2, so there's an x-intercept. And set this equal to 0, you'd get x equals negative 1. So those are the other x-intercepts. Negative 3 halves, 0, and negative 1, 0. So this implies that x plus 3 halves, x plus 1, and x minus 2 are the factors of f of x. Note that these two here are equivalent factors because they both give the same non-zero or the same 0, x equals minus 3 halves. All right, so using this remainder theorem in synthetic division. The remainder r, obtained in the synthetic division of some function by this binomial x minus k, provides the following information. 1. The remainder r gives the value of the function at that given k. That is, f of k is equal to the remainder. If the remainder is 0, x minus k is a factor of f of x. If the remainder is equal to 0, k, 0, whatever this number is, without the minus sign, k, 0 will be an x-intercept of that graph. So here in the huddle, we got 4 of them. The first 2 are use synthetic division to divide these. That'll be much easier than the polynomial stuff. Don't forget here you will have some placeholders. Down here for 56, use the remainder theorem and synthetic division to find each function value. Verify with the other method. And for this one, let's just do, I think I might cut out the C and the D part. That gets a little bit redundant. So what you could do is synthetically divide this by 2 and then see what your remainder is. That should be the same as if you just take this 2 and plug it right in and see what pops out of the function. Same thing here for B, g of 1. Let's see here, 67 is verify the factors, find the remaining factors, use the results for the complete factorization. So it's just like the last example. Here is a function. Here are 2 given factors. Use synthetic division to divide them out and find the remaining factor. So pause the video and give those a try. Start her back up and see if you got them. Okay, let me move a little bit of this down here until we need it. The first one, nice, pretty simple synthetic division. Let's get all set up here. We're starting with 5x cubed plus 18x squared plus 7x minus 6. So we have no placeholders. All powers of x were accounted for, 3, 2, 1. And we are dividing that by the quantity or the factor x plus 3. So we would think about that as x minus a negative 3. Do our line here and bring down the 5. Negative 3 and 5 is negative 15, and we add. Negative 3 times that 3 is negative 9, add negative 2. Multiply those, we get a positive 6. So there is no remainder. So the division of that, again, we would need to put some variables in there. We started out with a cubed. We divided by x to the first. Well, that turns out to be an x squared. 5x squared plus 3x minus 2, 0 remainder. This one's going to be a little different, kind of interesting here. Look at that numerator. It is a single term. But if we think about it here, we're going to start with a minus 3x to the fourth plus 0x cubed plus 0x squared plus 0x plus 0. Wow, that's a lot of zeros. And we are going to divide that by our denominator, x plus 2. Again, swap that sign out. It will be a minus 2. Bring down the minus 3. Multiply here, positive 6. We add 6. Negative 2 times that will be a minus 12. And we add minus 12. Negative 12 or negative 2 times that will be a positive 24. This is interesting. And we add and get 24. Negative 2 times that is minus 48. And that will be our remainder. So I guess I can do this. So we started out with fourth power. We divided by a first power. Well, that leaves us with a cube. Minus 3x cubed. Cubed, I said cubed, and I wrote squared. Plus 6x squared. Minus 12x. Plus 24. With a remainder of minus 48 over the divisor, x plus 2. So there we go. That's kind of an odd one, but we've never done one like that before. We divided that just a single term, minus 3x to the fourth. So we needed all those placeholders in there. That would be an interesting one to FOIL it back out and see all those middle terms cancel. So you're only left with a minus 3x to the fourth. Okay, example 56, we're going to do a little remainder theorem. Use that and synthetic division to find each value. Verify your answers with another method. Again, doing 2 of these will be enough. So here we are going to be dividing into this. Let's set it up for synthetic division, taking note of our placeholders. So we have a 2x to the sixth. There is no x to the fifth power, so that'll be a placeholder 0. For the fourth power, we have a 3. For the third power, there's nothing, so that'll be a 0. And then we have a squared, that'll be a minus 1x squared. And then a 0x, and then our constant of 3. So let's double check here. So that is the sixth power, sixth, fifth, fourth, third, second, first power, and then our constant 3 is at the end. So we are all accounted for there. We're going to divide that by 2. So we bring down the 2. 2 times 2 is 4, and we add. 2 times 4 is 8, and we add those. 2 times 11 is 22, and we add those. 2 times 22 is 44. We add those, so that's a 43. 2 times 43, that's an 86. We add those. 2 times 86, let's see, that's 160 plus 12, 172. And we add that, and we get 172, and 3 is 175. So there is our remainder r. And we should be able to verify that by plugging this 2 in for x. We're going to do g of 2, so just run a 2 through the function, and hopefully we'll get that same 175. So g of 2, that is going to be 2 times 2 to the sixth plus 3 times 2 to the fourth minus 2 squared plus 3. I do need a little more room here, and I guess the only thing we really need to keep there is that remainder 175, because hopefully this is all going to work in the end. Get over there. Why is it not letting me get that G? Got it. Okay. So 2 times 2 to the 6, 2 to the 5th is 32. So that would be 32 times 2, or 64. Plus 2 times, or 2 to the 4th is 16. 16 times 3 is 48. Minus 2 squared is 4, and a plus 3. 2 times 64 is 128. Plus 48. Well, if I add those two together right now, that's a 160. 176 minus 4 and a plus 3 nets out to a minus 1. 176 minus 1 is 175. So that way we did synthetic division first, got the remainder, and then evaluated the function at that g of 2, and we saw that they did match up nice. Well, let's reverse that for the next one. G of 1. Well, if I do g of 1 and I run a 1 through the function, this will be a little easier. 2 times 1 to the 6th plus 3 times 1 to the 4th minus 1 squared plus 3. Well, any 1 to this power is going to be 1. 1 times 2 is 2, plus 1 to the 4th is 1, times 3 is 3, minus 1 squared is 1, plus 3. So let's see, we have 5 minus 1 is 4. 4 plus 3 is 7. So when we synthetically divide, we should have a remainder of 7. So we got to set up that coefficients again for our division. 2x to the 6th, 0x to the 5th, 3x to the 4th, 0x cubed, minus 1x squared, 0x, plus 3. Now we are dividing that by 1. That wasn't a very good horizontal line. That's a little better. Bring down the 2. 1 times 2 is 2, and we add. 1 times 2 is 2, and we add. 1 times 5 is 5. We add. 1 times 5 is 5, and we add and get a 4. 1 times 4 is 4. We add that and get a 4. 1 times 4 is 4, and we add that and get a 7 as our remainder. There it is. All right, last one. This is just like the final example, where they gave us a couple factors to get us started, and they want us to completely factor this. And actually, after we divide these two out, we should just be left with one factor, because here's an x, and here's an x, and this is x cubed. So we'll divide out once and get an x squared, divide out again and get an x to the first power. So the clues they gave us will be plenty enough. Let's see here. Synthetic division. We'll set up our coefficients. 2x cubed, 1x squared, minus 5x, and a plus 2. No placeholders required. Now these are factors in parentheses, so we want x minus h, or minus a negative. So we want to divide this by a negative 2. So bring down the first 2. We multiply here and get a negative 4, and add to a negative 3. Multiply there and we get a positive 6, add to a positive 1. Negative 2 times 1 is negative 2, and that goes to a remainder of 0. So when we factor out the x plus 2, we're left with 2x squared minus 3x plus 1. We want to take that 2x squared minus 3x plus 1 and divide that by this factor. So we're going to divide here by a positive 1. And we bring down the 2, multiply to a 2, and we add negative 1. Multiply here, negative 1, no remainder. So let's see, our factors, the 2 they gave us were x plus 2 and x minus 1. And what are we left with here? Oop, that's not very good. Back that up. Our remaining factor, why is that doing that? There we go. Here would be 2x minus 1. 2x minus 1. Again, we could FOIL this out and then FOIL again, so to speak, here and get back to this original polynomial. Well, that's the end of 3.3, polynomial and synthetic division. Tonight's homework is a worksheet. Again, I'm not sure exactly what problems are somewhere out of this mess. Check my teacher website, or maybe I gave that to you in class.